Download this code from codegive.com, link in the description below. OK, let's dive into byte stuffing and bit stuffing, two techniques used in data communication protocols to prevent control characters or bit patterns within the data from being misinterpreted as control signals. We'll cover the concepts, differences, advantages/disadvantages, and code examples. Introduction, the problem. In many communication protocols, certain characters, in byte-oriented protocols, or bit patterns, in bit-oriented protocols, are reserved for signaling control functions. For example, *start of frame, SOF marks the beginning of a data frame. *end of frame, EOF marks the end of a data frame. *escape, ESC used to escape or negate the meaning of the following character. The problem arises when the actual data you want to transmit contains these same characters or bit patterns. If these data control characters or patterns are not handled correctly, the receiver might mistakenly interpret them as actual control signals, leading to synchronization issues, data corruption, or premature termination of the frame. Solutions: byte stuffing and bit stuffing. Byte stuffing, also known as character stuffing, and bit stuffing are two common techniques to address this issue. 1. Byte stuffing * used in byte-oriented protocols. It involves inserting an extra escape byte, ESC, before any occurrence of a control byte in the data stream. If the escape byte itself occurs in the data, it's also escaped. 2. Bit stuffing * used in bit-oriented protocols. It involves inserting an extra 0 bit after a specific number of consecutive 1 bits in the data stream. This ensures that the control bit sequence, often a string of ones, cannot accidentally appear within the data. 1. Byte stuffing, character stuffing. Concept * introduce an escape character, ESC, before any control character that appears in the data stream. The receiver removes the ESC character to recover the original data. If the escape character itself appears in the data, it is also escaped by inserting another escape character before it. Characters involved *. Data * the actual payload to be transmitted. Flag * the byte used to indicate the start and end of a frame, example 0x7e. Escape, ESC a special byte used to signal that the following byte should be interpreted as data, not a control character, example 0x7d. Encoding / stuffing process * 1. Scan the data for any occurrences of the flag or ESC characters. 2. If either flag or ESC is found, insert an ESC byte immediately before it. 3. The flag byte indicates the beginning and the end of frame, so it will only be inserted at these two spots. 4. If any of the flag or ESC is present in the data, the insert will proceed. 5. The data is now stuffed. Transmit the stuffed data along with the start and end flag. Decoding / unstuffing process * 1. Receive the data stream. 2. Scan the data for ESC characters. 3. If an ESC is found. If the following byte is either flag or ESC, remove the ESC. The following byte is the original data. If the following byte is not flag or ESC, it indicates that the data is corrupted. 4. Remove the start and end flag bytes. 5. The remaining data is the original data. Example *. Let's say flag equals 0x7e. ESC equals 0x7d. Data to transmit 0x10 0x7e 0x20 0x7d 0x30. Stuffed data 0x7e 0x10 0x7d 0x7e 0x20 0x7d 0x7d 0x30 0x7e. Here's how the stuffing happened. 1. The first 0x7e is the flag to start a frame. 2. 0x10 is part of the actual data, so it's transmitted as is. 3. 0x7e is a flag character found in the data. We insert an ESC, 0x7d, before it, 0x7d 0x7e. 4. 0x20 is part of the actual data, so it's transmitted as is. 5. 0x7d is an ESC character found in the data. We insert an ESC, 0x7d, before it, 0x7d 0x7d. 6. 0x30 is part of the actual data, so it's transmitted as is. 7. The last 0x7e is the flag to end a frame. Asterisk C++ code example asterisk. Asterisk advantages of byte stuffing asterisk. Asterisk simple to implement. Asterisk works well with byte-oriented protocols. Asterisk disadvantages of byte stuffing asterisk. Asterisk overhead, can significantly increase the size of the data being transmitted, especially if the data contains frequent occurrences of the control characters. Asterisk less efficient for bit-oriented protocols. 2. Bit stuffing. Asterisk concept asterisk insert a 0 bit after a predefined number of consecutive 1 bits appear in the data stream. The receiver removes this inserted 0 bit during decoding. The sequence of consecutive 1 bits is often used as a flag, example 011111110. Asterisk bit sequence involved asterisk. Asterisk data asterisk the data stream to be transmitted. Asterisk flag sequence asterisk the bit pattern used to indicate the start and end of a frame, example 0111110, which has 6 consecutive ones. Asterisk stuff bit asterisk the 0 bit inserted after a certain number of consecutive ones. Asterisk encoding / stuffing process asterisk. 1. Scan the data bit by bit. 2. Count the number of consecutive 1 bits encountered. 3. If the number of consecutive 1 bits equals the predefined limit, example 5 in HDLC, insert a 0 bit immediately after the 5th one. 4. Reset the counter of consecutive ones. Asterisk decoding / unstuffing process asterisk. 1. Receive the data stream. 2. Scan the data bit by bit. 3. Count the number of consecutive 1 bits. 4. If the number of consecutive 1 bits reaches the predefined limit, example 5, remove the following 0 bit. 5. Reset the counter of consecutive ones. Asterisk example asterisk. Let's say asterisk flag sequence 0111110, 6 consecutive ones. Asterisk the predefined limit for consecutive ones before stuffing is 5. Asterisk data to transmit, after framing 011111111100111111010. Stuff data, 011111001111001111010. Here's how the bit stuffing happened. 10111111, 5 consecutive ones. Insert a 0, 011110. 20111111, 5 consecutive ones. Insert a 0, 011110. 30011111, 5 consecutive ones. Insert a 0, 00111110. 410, 2 bits, so nothing is inserted. Asterisk C++ code example asterisk. Asterisk advantages of bit stuffing asterisk. Asterisk more efficient than byte stuffing in bit-oriented protocols, as it only adds 1 bit at a time. Asterisk less overhead compared to byte stuffing, especially when control characters are frequent. Asterisk disadvantages of bit stuffing. Asterisk more complex to implement than byte stuffing. Asterisk not suitable for byte-oriented protocols. Key differences summarized. Feature: byte stuffing, character stuffing, bit stuffing. Orientation: byte-oriented, bit-oriented. Stuffing: unit byte, character, bit. Stuffing: trigger control byte encountered predefined number of consecutive ones. Overhead can be higher if control bytes are frequent. Lower, adds only one bit at a time. Complexity: simpler, more complex. Example protocols: PPP, BySync, HDLC, SDLC. Choosing the right technique. The choice between byte stuffing and bit stuffing depends primarily on the underlying data communication protocol. Asterisk use byte stuffing if you are working with a byte-oriented protocol, where data is transmitted in units of bytes, and simplicity is a priority. Asterisk use bit stuffing if you are working with a bit-oriented protocol, where data is transmitted as a continuous stream of bits, and efficiency is important. Common protocols that use these techniques. Asterisk byte stuffing. Asterisk PPP, point-to-point protocol, uses byte stuffing to escape control characters in its frames. Asterisk BySync, binary synchronous communications, an older IBM synchronous protocol that employs byte stuffing. Asterisk bit stuffing. Asterisk HDLC, high-level data link control, a common bit-oriented protocol used in various applications, including X.25 and frame relay. Asterisk SDLC, synchronous data link control, an older IBM bit-oriented protocol, a predecessor to HDLC. Asterisk Ethernet. Asterisk uses a variant of bit stuffing, but the details differ slightly. Important considerations. Asterisk error handling. Asterisk in real-world implementations, error detection and correction mechanisms, example checksums, CRCs, are often used in conjunction with stuffing techniques to ensure reliable data transmission. Asterisk synchronization. Asterisk the receiver needs to be able to synchronize with the beginning of a frame to properly decode the data. The flag sequence in both byte stuffing and bit stuffing protocols helps with this synchronization. Asterisk performance. Asterisk the overhead introduced by stuffing techniques can impact the overall throughput of the communication channel. Careful design and optimization are necessary to minimize this impact. I hope this comprehensive explanation clarifies the differences between byte stuffing and bit stuffing. Let me know if you have any further questions. Byte stuffing versus bit stuffing, a comprehensive guide with code examples. Both byte stuffing and bit stuffing are techniques used in data communication protocols to handle the occurrence of special characters, or bit patterns, within the data stream that could be misinterpreted as control characters, like frame delimiters or escape sequences. The purpose is to ensure data integrity and prevent premature frame termination or incorrect interpretation of data. However, they operate on different levels. Byte stuffing works on byte, character, boundaries, while bit stuffing works on individual bits. Here's a detailed breakdown. 1. The problem: why stuffing is necessary. Imagine a protocol where frames are delimited by a special byte sequence, like 0x7e, a common example in HDLC. If the actual data payload itself happens to contain 0x7e, the receiver might prematurely think the frame is over, leading to data corruption. Similarly, if a protocol uses a special escape character, example 0x7d, to indicate that the following byte is a control character that should be interpreted literally, the escape character itself needs to be protected. 2. Byte stuffing, Character stuffing. Asterisk what it is asterisk byte stuffing, or character stuffing, inserts an extra byte, the escape byte, before a special character if that special character appears within the data payload. The receiver, upon encountering the escape byte, knows to interpret the next byte literally, rather than as a control character. Asterisk how it works asterisk. 1. Identify special characters asterisk the protocol defines specific byte values, example 0x7e for frame delimiters, 0x7d for escape character itself, that need to be protected. 2. Sender, encoding. Scans the data payload byte by byte. If a special character is found, it inserts the escape byte, 0x7d, before the special character. It might also modify the special character itself after the escape byte to distinguish it from a true control character. For example, 0x7e might be replaced with 0x7e:0x20, XORed with 0x20, after the escape byte. 3. Receiver, decoding. Scans the received data byte by byte. If it encounters the escape byte, 0x7d, it knows the following byte is not a control character but a literal data byte. It removes the escape byte and, if applicable, undoes the modification done by the sender, example XORing with 0x20 again. Asterisk example asterisk. Let's say frame delimiter, 0x7a. Escape character, 0x7d. Transformation, special character is XORed with 0x20 after escape. Original data, 0x41 0x7e 0x42 0x7d 0x43, a. Frame delimiter, b. Escape character, c. Stuff data, 0x41 0x7d 0x5e 0x42 0x7d 0x5d 0x43, a. Escape, XORed frame delimiter, b. Escape, XORed escape character, c. Explanation of stuff data. 0x7e is replaced with 0x7d 0x5e, 0x7ex or 0x20 equals 0x5e. 0x7d is replaced with 0x7d 0x5d, 0x7dx or 0x20 equals 0x5d. Asterisk code example, Python. Asterisk advantages of byte stuffing asterisk. Simple to implement in software and hardware. Works on byte boundaries, making it easier to process in many systems. Asterisk disadvantages of byte stuffing asterisk. Inefficient if special characters appear frequently in the data. It increases the overhead proportionally to the number of special characters. Protocol specific, the escape character and transformation need to be defined within the specific protocol. 3. Bit stuffing. Asterisk what it is asterisk bit stuffing inserts an extra bit into the data stream after a specific sequence of consecutive bits. This technique is used to prevent long strings of the same bit, usually consecutive ones, from being misinterpreted as control signals, like flags, or clock synchronization patterns. Asterisk how it works asterisk. 1. Define the stuffing pattern asterisk the protocol defines a specific sequence of bits, example 5 consecutive ones, that trigger the insertion of a 0 bit. 2. Sender, encoding. Scans the data bit by bit. Counts consecutive ones. If the defined stuffing pattern is found, example 5 consecutive ones, it inserts a 0 bit after the 5th one. 3. Receiver, decoding. Scans the received data bit by bit. Counts consecutive ones. If the stuffing pattern with the inserted 0 is found, example 5 ones followed by a 0, it removes the inserted 0. Asterisk example asterisk. Let's say. Stuffing pattern, 5 consecutive ones. Original data, 11111010111111 1011111. Stuffed data, 11111010111111 1011111. Explanation of stuffed data. After the first sequence of 5 ones, a 0 is inserted. After the second sequence of 5 ones, a 0 is inserted. The last sequence of 3 ones does not trigger stuffing because it's less than the 5 consecutive ones required. Asterisk code example, Python. Asterisk advantages of bit stuffing asterisk. More efficient than byte stuffing when the special sequences are rare. The overhead is directly related to the frequency of the stuffing pattern. Hardware friendly. Can be implemented with shift registers and simple logic gates. Asterisk disadvantages of bit stuffing asterisk. More complex to implement in software than byte stuffing. Requires bit-level manipulation. Can increase data transmission time compared to byte stuffing, although less so if stuffing is infrequent. 4. Key differences summarized. Feature byte stuffing bit stuffing. Level of operation byte level bit level. Stuffing unit byte, character, bit. Trigger special byte value specific bit pattern, sequence of bits. Implementation complexity simpler, in software, more complex, in software. Overhead higher if special bytes are frequent, lower if the stuffing pattern is infrequent. Hardware implementation relatively simple, easier with dedicated hardware logic. Use cases older protocols, simpler systems protocols requiring high reliability like HDLC, SDLC, and Ethernet's AUI. Examples: BySync HDLC, high-level data link control, SDLC, synchronous data link control, Ethernet's attachment unit interface, AUI. 5. When to use which? Asterisk byte stuffing asterisk. When simplicity is paramount and the overhead of byte stuffing is acceptable. In older protocols or systems where byte-oriented processing is the norm. When you need to handle special characters directly and byte-wise. Asterisk bit stuffing asterisk. When high reliability and data integrity are critical, especially in high-speed communication. When the cost of stuffing overhead needs to be minimized and the stuffing pattern is relatively rare. In protocols designed for bit-oriented transmission and hardware-optimized implementations. In summary asterisk. Both byte stuffing and bit stuffing are valuable techniques for maintaining data integrity in data communication systems. The choice between them depends on factors such as protocol requirements, performance considerations, and implementation complexity. Byte stuffing provides a simple, byte-oriented approach, while bit stuffing offers better efficiency when the stuffing pattern is infrequent and bit-level manipulation is feasible. Understanding the trade-offs between these techniques is essential for designing robust and reliable communication systems. Okay. Let's dive deep into the world of byte stuffing and bit stuffing, two crucial techniques for ensuring reliable data transmission across communication channels. I'll provide detailed explanations, illustrate the concepts with code examples in Python, and cover the nuances of when and why each technique is used. The problem: framing and synchronization. Imagine you're sending a series of packets over a network. How does the receiver know where one packet ends and the next one begins? How does the receiver maintain synchronization with the sender to correctly interpret the bits or bytes? That's where framing comes in. Framing involves adding special signals, often delimiters or flags, to the data to mark the start and end of a packet or frame. The problem is that sometimes the data itself might contain those special delimiter patterns. If the receiver sees one of these patterns within the data portion, it might mistakenly think that the packet has ended prematurely or that something unexpected has happened. This leads to data corruption and misinterpretation. Byte stuffing and bit stuffing are solutions to this problem. They modify the data to prevent these accidental delimiters from occurring within the data. 1. Byte stuffing, character stuffing. Concept byte stuffing works by inserting, or stuffing, an extra byte into the data stream whenever a special delimiter byte is encountered within the actual data. The receiver, upon detecting this extra byte, knows to remove it and interpret the original byte correctly. Common scenario often used in asynchronous serial communication protocols, example RS-232 with PPP/HDLC framing. Example let's say we use 0x7e, 126 in decimal, character in ASCII, as the frame delimiter, the flag byte, to mark the start and end of frames. And let's say 0x7d, 125 in decimal, character in ASCII, is an escape byte that signals that the following byte has been stuffed. If the data contains 0x7e, we replace it with 0x7d 0x5e. 0x5e is 0x7e XORed with 0x20. If the data contains 0x7d, we replace it with 0x7d 0x5d. 0x5d is 0x7d XORed with 0x20. Advantages relatively simple to implement. Works well in byte-oriented communication systems. Disadvantages overhead, stuffing extra bytes increases the size of the transmitted data, potentially reducing throughput. Limited to byte-oriented systems, not suitable for protocols that transmit data in bit streams. Python code example Explanation of the Python code one constants flag _byte, escape _byte, and XOR value are defined for clarity and ease of modification. The XOR is just one possible way to transform the stuffed character. 2 byte stuff, data, function iterates through each byte of the input data. If the byte is equal to flag _byte or escape _byte, it inserts escape _byte followed by the original byte XORed with XOR value. Otherwise, it simply appends the original byte to the stuffed data. Finally, it converts the byte array to bytes and returns it. 3 byte unstuff, data, function iterates through the stuffed data. If it encounters escape byte, it knows the next byte is a stuffed byte. It advances the index I, XORs the next byte with XOR value, and appends the result to unstuffed data. Otherwise, it appends the byte directly to unstuffed data. Includes error handling for a dangling escape byte at the end of the data. For example usage the code demonstrates how to use the byte stuff and byte unstuff functions with sample data. It prints the original, stuffed, and unstuffed data in hexadecimal format. 2. Bit stuffing. Concept bit stuffing works by inserting an extra bit into the data stream whenever a specific bit pattern is encountered, example 5 consecutive ones. The receiver detects this extra bit and removes it to reconstruct the original data. Common scenario used in bit-oriented protocols like high-level data link control, HDLC, synchronous data link control, SDLC, and controller area network, CAN. Asterisk example asterisk assume we want to prevent the occurrence of 5 consecutive ones within the data. Asterisk whenever the sender encounters 5 consecutive ones in the data, it inserts a 0, a stuffed bit. Asterisk the receiver, upon detecting 5 consecutive ones followed by a 0, removes the 0. Asterisk advantages asterisk. Asterisk more efficient than byte stuffing in terms of overhead, especially when the probability of the special bit pattern is low. Asterisk suitable for bit-oriented protocols. Asterisk disadvantages asterisk. Asterisk more complex to implement than byte stuffing, requires bit-level manipulation. Asterisk Python code example asterisk. Explanation of the Python code asterisk. 1-bit_stuff, data, function asterisk. Asterisk iterates through each bit, represented as a string character 0 or 1, in the input data. Asterisk maintains a count of consecutive ones. Asterisk if count reaches 5, it inserts a 0 into the stuffed underscore data and resets count to 0. 2-bit_unstuff, data, function asterisk. Asterisk iterates through the stuffed underscore data. Asterisk maintains a count of consecutive ones. Asterisk if count reaches 5, it skips the next bit, which should be the stuffed 0, and resets count to 0. Critically, it advances the index I to skip the stuffed bit. 3 example usage asterisk the code demonstrates how to use the bit_stuff and bit_unstuff functions with sample data. Key differences summarized. Feature byte stuffing bit stuffing. Dash 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 dash. Data unit bytes bits. Scenario byte-oriented protocols bit-oriented protocols. Overhead potentially higher potentially lower. Complexity simpler more complex. Common uses RS-232, PPP/HDLC framing, HDLC, SDLC, CAN. Delimiter type special byte value, example 0x7e, specific bit pattern, example 5 consecutive ones. When to use which? Asterisk byte stuffing asterisk choose byte stuffing when your communication system is inherently byte-oriented, transmitting data in units of bytes, and the implementation complexity is a significant concern. The overhead might be acceptable in scenarios where bandwidth is not extremely limited. Asterisk bit stuffing asterisk choose bit stuffing when your communication system is bit-oriented, and you need to minimize overhead. It's typically preferred in higher speed protocols where bandwidth efficiency is crucial, and the added complexity is manageable. Important considerations asterisk. Asterisk error handling asterisk in a real-world system, you'd need to add error detection and correction mechanisms, example checksums, CRC, in addition to stuffing. Stuffing prevents framing errors, but it doesn't guarantee perfect data integrity. Asterisk synchronization asterisk stuffing techniques typically rely on the receiver being synchronized with the sender. If synchronization is lost, the unstuffing process will fail, leading to corrupted data. Protocols often include mechanisms for re-establishing synchronization. Asterisk performance asterisk the performance impact of stuffing should be considered, especially in high-throughput applications. The stuffing and unstuffing processes add computational overhead. Asterisk choice of delimiters/patterns asterisk carefully select the delimiter byte, S, or bit pattern to minimize the frequency of stuffing and optimize bandwidth utilization. By understanding the principles of byte stuffing and bit stuffing, you can design more robust and reliable communication systems that can gracefully handle the challenges of transmitting data over noisy channels. Remember to choose the technique that best suits the specific requirements of your protocol and application.